In this demonstration, we're going to take a sneak preview at NX12, together with some current technology such as topology optimization and convergent modeling. Reducing weight, material usage, and also reducing assembly complexity are all valid reasons for using design topology optimization. Here you can see in the graphics window a pipe assembly, which is made up of 3 sections that are bolted together. What we'd like to do is to use topology optimization to reduce the complexity of the assembly whilst maintaining the structural characteristics of the pipe assembly. The first thing we'll do is to open up the part that we're going to use for our optimized design. What you can see on the screen is the internal bore structure modeled as solid bodies, together with some keep in and keep out areas. As previously mentioned, part of this demonstration is a sneak preview at NX12. And one of the key enhancements of NX12 is the ability to have multiple display parts. You can see in the top left hand corner of the graphics window 2 tabs. The one that's highlighted with a darker background is the current displayed part, our topology optimized part. The other one is our original assembly. But what we can do is to drag our original assembly tab into the center of the screen and then position it using one of the direction arrows. So what we end up with are 2 displayed parts side by side. You can see that now the window on the right is our active window, as the tab at the top is highlighted with a dark background. What you'll also notice are that all your navigators now correspond to this active window. So your part navigator, your assembly navigator will relate to everything that's in the active window. To make the other graphics window active, it's just a simple case of selecting anywhere in that window. And now you'll notice that the assembly navigator has changed to reflect the geometry that's in our new active window. The next step is to open up the part navigator and bring back the geometry that defines the design space or design volume for our topology optimization. This design space is literally the volume that our new design must reside within. So let's go through the process of setting up the topology optimization. So we start by activating the topology optimization tab, and then we're presented with all the tools needed to set up the topology optimization. The setup is very straightforward. All we need to do is move from left to right along the set of tools in the topology optimization toolbar. We start by selecting the design space and then specifying the material. We then move on to looking at the optimization features, which in this case are the solid bodies that represent the bores in the pipework. Some of these have thickness and are also defined as either keep out areas, keep in areas, or shells. We're also able to manage load cases. In this case we only have the one load case, but it combines a number of different pressures on the individual bores within the part that's to be optimized. Finally, we can set up the parameters for the optimization run itself. Inside of here we can define the resolution. The more coarse the resolution, the faster the optimization, and consequently the finer the resolution, the longer the optimization will take. We can also specify a mass target here as well, and then we run the optimization. The optimization consists of 3 specific stages: a rough initial pass followed by a refining pass, and you can see both being illustrated in the progress bar, and then finally there's a meshing stage, and this is where the optimization body is created. Notice that when we hide the optimization features, we're left with one single body as opposed to a number of components in the original assembly. The resultant body is a facet body, and we will use convergent modeling technology to make further changes to our generative design. But first, let's take a look at the maximum displacement and maximum stress in our newly generated design. We're able to do this within the topology optimization toolset, as topology optimization itself is based on CAE technology. Here you can see we can quickly look at the maximum displacement and maximum stress in our new component. As previously mentioned, the resultant body is a facet body, and for us to effectively work with it inside of NX, we're going to convert it to a convergent body. So we activate our reverse engineering toolset, and inside of here we have a command that allows us to convert the facet body to a convergent body. You can see that we're working with a solid form as we section the body. You've already seen some of the new functionality that's going to be coming with NX12 with the use of multiple display parts. The topology optimization that we've used is available right at this moment with NX1101. So let's take a look at some new and exciting ways that you can interact with facet bodies that will be coming with NX12. Convergent modeling technology inside of NX enables the design engineer to work directly with facet geometry. The capabilities of convergent modeling have been greatly enhanced in NX12 to provide even more powerful features for working with facet geometry. Currently, convergent modeling technology has enabled the design engineer to use tools such as Boolean operators, offsets, projections when working with facet geometry. But what about if we actually want to select the facet geometry directly and make some changes to it? NX12 will provide this powerful capability with tools such as Create Transition, which we will take a look at here. There are two transition types. There's either blend or chamfer, and we will take a look at both. The first one we'll take a look at will be chamfer. Both transition types can be open or closed. In this case we will use the closed option, and what this means is that NX will look to automatically close off the transition boundary based on the geometry selected. The user interaction is straightforward. You just select points around the edge of the area that you want to transition. And when NX has enough information, it automatically completes the boundary and creates, in this case, the chamfered transition. This is a very flexible and powerful way of being able to modify a facet body directly. So let's take a look at the other transition type, the blend. In this case we're going to transition the intersection area where the two balls meet. Again, we simply select around the edge of the intersection and then let NX complete the transition. So again you see a very powerful way of working directly with facet bodies. And without convergent modeling technology, this would be very time consuming and difficult to achieve. Finally, let's take a look at two other enhancements that are coming with NX12. First will be to do with selection, and the second will be a further enhancement to convergent modeling technology. So using multiple displayed parts, we have our new topology optimized part plus our original assembly side by side. And what I may want to do is to take some key location points off our original assembly and reuse them in my new topology optimized geometry. In NX12 it is now very simple to do that using drag and drop capability from one window to the other. So we activate the drag and drop between windows option, and then using the face selection filter we drag and drop one selected face from our original assembly into our new topology optimized component. We can now use this copied reference geometry to position some hole features we want to add. And bear in mind, this is facet geometry that we're adding these hole features to. So we selected the direction vector for the hole, we select the geometry that we want the hole to be subtracted from, and then we use the reference geometry to position the holes themselves. We will now hide the reference geometry so that we're only left with our facet body on the screen. And again, you can see the 4 hole features that have been added to the convergent body. And if we look in the part navigator, you can see that they are physical features that we could go back in and edit, change the size, change the type of. This is unique capability and would be impossible to do without convergent modeling technology. So let's just recap on what you've seen in this demonstration. You've seen how we've taken an existing assembly and using topology optimization, we've reduced the number of components and also the material usage, whilst maintaining the part is fit for purpose. We've then looked at some of the new technology coming with NX12, such as multiple display parts, and also enhancements to convergent modeling technology. You've seen how we were able to drag and drop geometry from one window to the other, and also how we can now use general NX features and incorporate those directly into a facet convergent body. The overall benefits of what you've seen are massive time savings and improvement in productivity when working with faceted geometry.